Hello everyone. In this video, we will continue to examine topic 5.4, the magnetic effects of electric currents, and in particular, we will continue to unpack the magnetic field due to a current-carrying wire. All right, in the last video, we introduced the magnetic field due to a current-carrying wire. Looks like this, and we can use the right-hand rule to determine the direction. The magnetic field consists of concentric circles or closed loops around that moving charge. The magnitude decreases with distance according to this formula. It is symmetric along the length of the wire, and it increases with the current. But this arrangement here is incredibly inconvenient to draw and a little annoying to deal with. So we have a different representation that we use when working with sort of two-dimensional cross cutouts. So you're not trying to draw these sort of isometric field loops. And we use what is known as Aeronate Notation. So we symbolize the magnetic field as if it were an arrow. It looks like this with its head and its sort of tail feathers. And so if the magnetic field is shown to be going into the board, it's as if you're looking at the back of the arrow, and so that's symbolized with an X. If the magnetic field is sort of coming out of the board or coming out of the page, it's symbolized with this sort of dot, and the dot indicates sort of looking at the front of the arrow. So the way this is supposed to work is that this looks like the front of the arrow, this looks like the back of the arrow. In other words, if you have the current going up the page, then on the left side of the wire here, according to the right-hand rule, that magnetic field is coming out of the page, and that's symbolized with these dots. On the right side of the wire, the magnetic field is going into the page, and that's symbolized with these X's. Notice that when I diagram the magnetic field, they are not equidistant. The field gets weaker as we go further out. And this doesn't show the field that sort of loops all the way around and sort of curls in front and behind of the current. But this is often an easier and more useful way of notating how the magnetic field around a current-carrying wire is in a particular region of space. So what would happen then if you reverse the direction of the current-carrying wire? If you direct the current-carrying wire down? Well, you stick your thumb in the direction of the current down the page. I know that sort of hurts your wrist, but totally fine. And then your fingers curl in the direction of the magnetic field, which means they're now going into the page or into the board on the left-hand side of this wire and out of the page or out of the board on the right-hand side of this wire. So take a moment and consider other orientations before moving on to the next slide. That is, what would it look like for left, for right, and what would it look like if the current were coming out at you or going into the page? Take a moment and sort of think about that and maybe do a couple sketches. You can pause the video right here and moving forward. So what happens if that current is going to the left? Well, if the current is going to the left and your thumb is going to the left, then it's going into the page or into the board above the wire and coming back out below it. That is exactly reversed if the current is going to the right. And for the magnetic field out, so what happens if your current is going out? Well, you can use the same representation for the current that you do for the magnetic field. So we represent the current coming out at us, and the magnetic field you would see then looks like this. These are concentric circles going in the counterclockwise direction. If your thumb is sort of pointed out at your face, then your fingers will curl in this direction as long as you are using your right hand. Those of you who are left-handed, I apologize. You will want to get used to using your right hand for this particular subunit. Same for in. So if you go in, notice it just simply reverses the directions of the magnetic field lines. One final note here, recall that magnetic field is a vector field, which means that the direction of the magnetic field is actually tangent to the field line, and the magnitude is related to the field density. So perhaps a better representation of the magnetic field would involve sort of these tangent arrows at every point, okay? And the strength of the field should actually be higher closer in. So actually, these arrows are backwards, which is something I'm going to fix right here. But I'm probably not going to re-record the video, so check back for the notes a little bit later. But basically, these arrows right here should be longer than these arrows on the outside. The arrows on the outside should indicate a lower field strength.